I'm ready. Yep.
All right. Today we have the second part of Bruno's talk. When can weakly coupled detectors harvest entanglement? Bruno, floor is yours.
Thank you, Ezra, for the introduction. So, as you may remember from last week, we started discussing this issue of entanglement harvesting with weakly coupled particle detectors, and a discussion that emerged in connection with the fuse-reverse framework for measurements in quantum fields. So, yeah, last week we mainly discussed a review of the main motivation for the subject, which has to do with how to conceptualize measurements in quantum field theory. We talked about the fuse-reverse framework and the Rouet model, which is a particular instance where the fuse-reverse framework was applied, in particular to the task of entanglement harvesting. We discussed some conclusions that were drawn from the Rouet model in terms of particle detectors, local particle detectors, defined in terms of local modes of a scalar field. And my main goal in this talk will then be to address exactly how mixed can local modes of a free scalar field be, and also how the mixedness that is present in these initial probes can impact quantitatively the entanglement harvested in a situation that we have more control over, which is the case of unrooted width detectors or unrooted width like detectors. So as last time, these will be the main references you should keep in mind when, in case you get interested about the subject. This last one is currently under a few modifications, but should be public soon. So yeah, so just as a quick review, the dynamics of a real scalar field, in this case I'm defining it as a minimally coupled scalar field, but at that point it didn't really have to be. But it can be defined through this action, which, as you all know, leads to the Klein-Gordon equation. That is the equation of motion for the field. And given the field, you can define any local mode of the field by essentially smearing it with some smearing function or a pair of smearing functions that can be chosen to be compactly supported inside the localization region that you're interested in talking about, and can also be chosen such that these quadrature operators satisfy canonical commutational relations for position and momentum. So they define a single mode of a harmonic oscillator, right? Now, given any local region on spacetime, what we are interested in here is to look for the minimally mixed mode that will be defined in terms of these two canonically conjugated operators that I'm calling V and W here. And we will investigate the mixedness of such mode for a general global thermal state of the field labeled by inverse temperature beta. So I'm implicitly assuming that we're in a regime where these statements of global state of the field with some well-defined temperature make sense. And yeah, that's pretty much it. So in other words, we're going to be looking for some measure of mixedness that I'm defining here as S. And we are basically dealing with an optimization procedure in which we look for the minimum of such measure of mixedness under these constraints. So V and W are on the span of the field operator, let's say, along some localized region, and they commute to I times the identity. And without loss of generality, we can take these modes, we can take these quadrature operators to be such that their expectation values are 0. The expectation value of the anti-commutator is also 0, and that the variances of both of them are equal. For those familiar with Gaussian quantum mechanics, this basically amounts to going to the basis of normal modes, let's say, of the span of the field within that region. So furthermore, we'll choose the measure of mixedness to be defined as this. So the expectation value of the sum of the square of the quadrature operators that we'll be calling the objective function. Again, this makes a lot of intuitive sense because since we can intuitively think of the VNW as defining a single mode harmonic oscillator, this is nothing more than the occupation number, or if you want, the energy of this harmonic oscillator. So it is bounded from below by 1, and we know also that it is only going to be equal to 1 if and only if the state of this mode is pure, right? So now, just for concreteness, to show the constructive proof that we're going to be talking about, we will take the case of flat space, and we will write the modes as spanned by field and conjugate momentum on a Cauchy surface for the region R, instead of smearing it also in time through the whole region R, which is something that you can always do by the time slice property of the QFT. And we're going to be labeling the characteristic size of the region by L. So this is basically the spatial extension of the region. It sets the scale for the spatial extension of the region of localization of the mode. Yeah, and we will take these modes then to be written explicitly like this as spatial integrals now over constant time surfaces, right? With these smearing functions, let's call it V and W, having support only within a ball of size L. Now we can just plug that back into the objective function, and given that we know the 2-point functions of the field and canonical momentum in flat space for any given temperature, you can give the expression for the objective function in terms of the Fourier transform of the spatial profile very straightforwardly. And now all that we're going to do is to present explicitly, in the case of one spatial dimension, but you shouldn't expect it to be much harder in general dimensions. We will show a sequence of functions that in the limits have u going to 1. So that basically says that you can make the mode as pure as you like for any temperature and for any spatial localization scale, even though, as we know from the Richelieu theorem, any local mode of a free scalar field will be mixed. So there's no non-trivial lower bound for the mixedness of the mode, is what we're trying to say. And yeah, for concreteness, this is how the constructive proof, let's say, works. We'll take this 2-parameter family of functions defined by this, where this function here is z, that is defining both profiles, say, is defined like this. There's a normalization constant that's just ensuring that z is L2 normalized, and this, yeah, there are 2 parameters here, this m and this kappa, and this function b here is the b-spline function, which is defined as the repeated self-convolution of the rectangle function, right? Yeah, over the domain from -1 to 1. Now this is just saying that it's defined to be supported with x from -L to L, right? Just to get a bit of intuition of what these self-convolution of the rectangle function do, they basically, of course, they don't change the support of the region, so it's always going to be supported between -L and L, or in this case, -1 to 1. And each self-convolution smoothens out the curve, basically. Now, if you remember here, we're doing, we're not just taking the b-spline function, we're taking products of cosines and taking derivatives. The cosines just to select a privileged wave number we label by the kappa, and the derivatives were just placed for technical reasons related to making the expressions converge in the IR, right? So yeah, now you can just compute the Fourier transform of that function, and that will be given by this, right? K squared again comes from the second derivatives. The convolution here comes from the convolution theorem for Fourier transforms, and Sm here is nothing but the Fourier transform of the self-convolution of the step function, of the rectangle function. So now the objective function can be written explicitly as this, where just for the sake of notation, I'm defining this expectation value under this probability distribution that's given by the modulo square of zeta tilde, so z, sorry, in momentum space. And now here comes, this is a plot of the power spectrum of z, or the absolute value squared of the Fourier transform of z, plotted from increasing values of both m and k, where lower values of m and k are closer to the center and higher ones are further away. So you can see that they, like, increasing kappa basically pushes them further apart, and increasing m basically means that they will decay faster when you move sufficiently far away from the peaks, right? Yeah, so from the equations that I had before, and also from the plots, you can expect that, you can see actually that this power spectrum has two peaks located at plus or minus kappa, and as I said, by increasing kappa, we can set them as far apart as we like. And also, you can see that away from the peaks, the power spectrum, so the function decays polynomially as a power of k, which decreases faster the higher the value of m is. So by increasing m, we can suppress the details outside of the peaks as much as we like as well. And that basically means that if we move m and kappa to a regime that's sufficiently high enough, so if we set m and kappa to be sufficiently high, we can make a mode such that the only regions that contribute to the objective function that we wrote before have the hyperbolic cotangent basically equal to 1, and we can approximate the average value, the expectation values of these omega k and inverse of omega k by their values at the center. Basically. So their values evaluated as k equals kappa. That can be done to arbitrary accuracy, and therefore we see that we can set up a sequence such that the value of the objective function, or that measure of mixedness, gets arbitrarily close to purity. So a perfectly pure mode, right? So yeah, in general, we can show, and I've not added this discussion here, but you can see it in the paper, that the behavior of the mixedness of any given mode for any fixed profile and for any temperature and localization scale of the region can qualitatively change depending on what particular shape you chose, and not just the size of the temperature. As an extreme example, something that is particularly easy to imagine is a situation on which you have, for example, a mode that occupies the whole space in an optical cavity, which we know can be given by a pure state if you're talking about the vacuum, for example. But you can pick such mode that is nonetheless entangled with another mode that's also supported in the whole cavity with some potentially different shape. And the point here is just that the bottom line is that just defining a size and a temperature for the ambient field is not enough to draw any more specific conclusions about the mixedness of the mode and how that would impact the particle detector. And there's also the fact that local modes of a free scalar field do not constitute a very reliable model for the setups that motivate most of the endeavors in particle detector models, the ones that we can find in quantum optics and atomic physics, for example. And therefore, we understand that the conclusions that can be drawn from such general features of modes of a free scalar field have limited impact on the actual task of entanglement harvesting with more realistic setups, more realistic probes, right? Now, the next step then is to see exactly how the mixedness of the probes impacts the entanglement that is harvested, now in a situation that we are more used to in the case of unrolled array detectors, right? because since the claims, part of the claims of the Ruwet paper were quite general and basically boiled down to the effect of mixedness on entanglement harvesting, it makes sense that those should be reproduced in the more controlled setup of unrelated detectors. So again, in the case of an unrelated detector, as we all know, each probe will be described by some localized quantum system around some fixed trajectory in space-time. And in particular, in the case of entanglement harvesting, we will have two probes that together couple to the field with an overall interaction action that is given by this, where this mu of tau here corresponds to an operator in the Hilbert space of each of the detectors. So in the case of a two-level system, that would be the sigma x or the monopole operator. And in the case of the harmonic oscillator, it could be, for example, the position operator. And lambda, this capital lambda, here is the space-time mirroring that sets the location or the support of the coupling in space and time, right? We'll, as usual, set up the initial state of the system of field and detectors in a fully uncorrelated state. And then we'll let the system evolve under the time of the interaction picture via this time evolution operator that's given by the time order exponential of some Hamiltonian that can be defined once you pick this time parameter according to which we'll evolve the system. Right? I didn't write explicitly what this time what this Hamiltonian is, but you all know that this is basically just picking the Hamiltonian density that shows up here in the action and integrating it not over space-time, but over constant values of this time parameter t. And now we'll choose to model the initial states of the probes as mixed states that in particular will be thermal with respect to their free Hamiltonian, right? So we'll take the initial state of the two probes as being a tensor product state, so they're uncorrelated, and furthermore, they are thermal states. This is not the most general mixed state that we could have, right? Because we are demanding that it is in particular a thermal state, not with respect to any Hamiltonian, but with respect to the same free Hamiltonian that basically labels ground excited states. But we believe that this is enough to illustrate the points we were trying to make, right? In the case of a two-level system, the state of each detector is then going to be given by something like this. And in the case of the harmonic oscillator, it will have the infinite tower of modes, in which in both cases we define this Boltzmann factor. We wrote everything in terms of the Boltzmann factor, the exponential of minus beta h, right? Or minus beta omega, where omega is the gap of the detector. Or in the case of the two-level system, it's the gap between ground excited. In the case of the harmonic oscillator, it's the gap between any two consecutive eigenstates of the free Hamiltonian. And the interesting thing here is that the purity of, in both cases, the purity of the two-level system in the harmonic oscillator has simple expressions in terms of Z, right? So we will be mainly interested in a low mixedness regime because that's the situation that we mainly expect that the usual conclusions from entanglement harvesting RQI with initially pure detectors will hold. And in this regime, the dependence of the purity on this Boltzmann factor is precisely the same, right? So it's 1 minus 2Z in both cases. Of course, it deviates if you go to higher powers, but we're going to be interested just in the first order in Z. And yeah, with trapped ions, for example, just for concreteness, fidelities of 0.99 are typical, and fidelities that are much higher can also be achieved, right? And this Boltzmann factor here is basically 1 minus the fidelity, or half of that. Look at it, the fidelity with the ground state. And so that means that it's safe to assume that in the setups that we would like to have the unrelated detector model and harvesting being a fair description of the setup, we can take that to be small. That's the main point. And if we take that to be small and we keep just the leading order contributions, in this Boltzmann factor. Then again, in both cases, both for the Arrow-Druid model with the two-level system and the harmonic oscillator case, the initial state of the two probes can be given by, is going to be written as this, right? And now you can carry out a Dyson expansion, the time evolution operator that we wrote earlier. And assuming that the field is in a state with vanishing one-point function, the first non-trivial contribution will come from second order in the couplings. Right? Now it's just doing the calculations to see what is the final state of the probes, and in terms of the canonical basis for both the harmonic oscillator for the two-level system in this case and the harmonic oscillator in this case, the matrix representation of the qubits and the harmonic oscillator is given by this, where the only difference that I want to highlight between this and the usual ones that you may have seen in vacuum entanglement harvesting with pure probes is this diagonal terms here that I labeled PA and PB, which just get a correction from the occupation number of each mode from the non-zero temperature, right? So this is the important bit. Everything looks identical to the case of pure probes, entanglement harvesting, except for a renormalization, let's say, of the populations of the first excited states. Now, as usual, in entanglement harvesting, a useful measure of entanglement that's used is the negativity, and it is defined for arbitrary dimensional Hilbert spaces. So I can just write down straightforwardly what the expression will be for both the harmonic oscillator and the two-level system in this case. And it turns out that the only potentially negative eigenvalue for the partial transpose, which gives negativity, can be written as this, right? It's this one. And the negativity, therefore, is just the maximum between minus this and 0. Right? Now, these p's were defined as their values with perfectly pure probes plus zi, and you can see that this E is monotonically increasing with the mixness parameters. So intuitively, it makes sense that any additional level of mixness will only decrease negativity, which is consistent with the claim that Rubat made, and it's also consistent with the basic intuition that mixness and local noise is bad for entanglement harvesting. Now, this simplifies further if you consider both Boltzmann factors to be the same, because basically then the difference here vanishes, the dependence on Z vanishes here, and you only have a sum of the Boltzmann factor here. And then the negativity just becomes a simple difference between the negativity evaluated with perfect probes and the Boltzmann factor of both of them. So this is a extremely simple relationship that sets the connection between a critical mixedness, so and the value of the amount of entanglement harvested in the case of pure probes. In particular, it sets very simply, right, what is the scale of mixedness above which you can no longer harvest entanglements perturbatively at lowest order and perturbation. You can also read it the other way around as defining for any sufficiently small value of initial mixedness. And sufficiently small here means that this perturbative expansion that I performed is a fair approximation. And you can see this as setting what is the critical coupling strength below which no entanglement is harvested. So remember that in usual entanglement harvesting scenarios, this lowest order negativity is proportional to lambda squared, right? So what this result is telling us is that basically the critical coupling strength scales as a square root of the Boltzmann function, which if you recover the expression in terms of the physical parameters of the probes, in particular its energy gap and the ambient temperature, is just this exponential dependence with 1/temperature. So in summary, what we did here was to present a response, let's say, to some of the claims made in this paper by Rueb in two basic fronts. First, we evaluated the mixness of local probes of a free scalar field, which was the main source of this inability of local weakly coupled particle detectors to harvest entanglement. And we also quantitatively evaluated at lowest order in perturbation theory what exactly is the value for the critical coupling strength for any initial value of mixedness such that no harvesting can occur at lowest order. Right? We saw that just setting a size or scale for the localization of the region where the modes are supported will typically be insufficient to characterize its mixedness, as there is no non-trivial lower bound for its mixedness, as we demonstrated. And this is true even though we know that any mode will be mixed. Right? As to the second point, we saw also that in the usual UDW kind of setup, the critical mixedness, or conversely, the critical coupling strength, can be computed in a very simple way at lowest order in perturbation theory. And that in low mixedness regimes, in particular, the critical coupling strength goes to 0 exponentially with 1/t, which gives us confidence that in setups that can potentially be achieved with actual experiments, this can be controlled and mitigated. So more generally, this helps us put into context some of the claims that were made by Rueb, inspired by the future framework, with regards to the ability of the models that are used currently in relativistic quantum information to be applicable to more realistic scenarios with realistic probes, right? And more broadly, I think it's worth saying that this will hopefully be just a first instance or one instance for the interplay between these different approaches to the measurement problem in QFT, both from the side of the rigor and of algebraic quantum field theory, and for the experimental appeal and proximity of the setups that we are used to dealing with in RQI. And hopefully this will lead to some further non-trivial consequences that are yet to be discovered. Right, so this is pretty much what I had. Thank you for listening, and I'm glad to take any questions.
All right, thank you, Bruno. So we take questions now, people. There are any questions for Bruno? Okay, there's one. Go ahead.
Hi. Yeah. Just a question about this kind of test functions that you're using. It's just I'm not very familiar with all this variety of choices there. The usual thing is to consider smooth and compactly supported, right? Or Schwarz functions if you want them to be non-compactly supported and all that. So I was wondering, is there any price to pay for using things that have corners and are not differentiable, or things like that? And because when you put the emphasis on that the shape of the test function matters, then you're also using shapes that have corners and stuff, I know that you can define distributions over these function spaces as well. I'm just wondering if there's anything to say about that.
Yeah, at this level, I don't expect much to change. I mean, we didn't prove a theorem about this being the most efficient way to achieve this minimal mixedness. So I guess in principle, you could try to reproduce the same sort of reasoning for smoother functions, right? But I don't expect much of the conclusion to change, right? The purpose of this B-spline function was basically to illustrate with a concrete example how you can set up a sequence of functions that can be made arbitrarily smooth, right? And that achieves the bound that we wanted. But I guess maybe Dan has something more to say about this.
So honestly, Maria, I don't understand the question quite well. What do you mean by price to pay? Because remember that we use this to prove that there's a limit of a sequence that satisfies this, right? We just don't need only one.
It's just yeah, sorry.
Sorry, you should reply to Eduardo and then I'll say my thing.
No, it's okay. No.
But what do you mean by the price to pay? Maybe that'll be clarifying.
I mean, in principle, I don't know. Formally, there is different distributions over these more exotic function spaces that can have these continuous functions. But I mean, maybe that's just like a technical thing. But I was wondering also when someone then would want to say that, okay, the shape of this might matter in more like physical terms. It might mean that you would have to physically motivate some kind of smearing function that has a corner. Yeah. And that might look weird or something.
That's actually what we used to criticize the model. Precisely that.
Yeah.
The model should not depend on the shape, you know.
or the model should include from atomic motivations a shape.
Right.
It should describe a state or it should be invariant to the state.
But the fun part is that the atoms are not that sensitive to the shape. If you do a model that models atoms, if you get a hard sphere with the right scale of atoms, or you get a realistic orbital distribution of the atoms, the results are qualitatively the same. It's not the case here. With the free modes of the field, no. That's one of the arguments we use against them.
Yeah, so the idea is that so the main idea, one of the ideas here was precisely that if you don't have a physical motivation to choose one particular profile or shape of the mode, then the conclusions that you can draw are very limited. And then the criticism follows that the RUEP model in particular is not a good model to realistic setups that motivate much of the particle detector models that we have. So yeah, this is where the model lies. But yeah, go on then.
Yeah, my one comment, if you can go to the sequence of B-spline functions, I think you had a diagram of them. One of the parameters there was M as opposed to kappa. When you increase M, you convolute the thing more with itself. And as you do this, it's made of piecewise functions, that all fit together. These are polynomials piecewise between, but the derivatives match up to a certain order. And as you keep increasing M, you match more and more derivatives at the joints. So these things become increasingly smooth as you increase M. And that's actually the limit that our sequence goes into. I think if you self-convolute the rectangle with itself enough, doesn't that give the bump function at the end of the day? Is that one? I don't remember that limit, right? I don't know. These things become smoother as you increase M, which is the regime we're looking in. And you can see that because the Fourier transform has its tails suppressed with increasing M.
Okay.
But in any case, Maria, there's no price to pay typically. That is the formulation price to pay, right? You mean in terms of divergences that may appear or ill definitions?
Yeah, I don't know. It's just that it's just very standard to consider the smooth compactly support. I mean, that's the definition I always find for test functions, and I'm just wondering. And I know that the distribution theory is very complicated, but
here we need just shapes, if you want, that are integrable against the Weidmann. That are in the test space of the Weidmann. Think of the Weidmann as a distribution. And the test space of that distribution, the ones where the integrals are well defined, that would work. That's what we need.
Okay. But also, Eduardo, when you're making the analogy of how some kind of space shape wouldn't matter in the Unruh de Witt case, then I'm thinking, okay, shape of what there? So here in the way you're treating the mixedness of the Unruh de Witt case to see if it affects entanglement harvesting, that kind of mixedness there doesn't have to do with any choice of shape of anything, right?
It's mixes that could come from wherever. We don't distinguish where it comes from. Yeah, any kind of mixedness.
Yeah.
I mean, we do make the particularization of it being from thermal sources, which based on experiments, that's typically where people worry about mixedness, right? But we don't need to particularize. We do the analysis in general. And then we also show the example to give scales of temperature and so on when that mixedness comes from the fact that the atom is hot.
One thing we did in the paper, which Bruno has left out of the presentation, was analyze when thermal mixedness is dominant over Richelieu mixedness for these free field modes.
But for the
And we-
modes, that's for the modes that we already
Yeah,
said.
for
For
the,
the modes,
for the local modes of a free field. And so we can see when, as you shrink the region down or cool it down, Richelieu starts to matter more. But in general setups, it's temperature that's important.
Yeah.
Okay.
Temperature makes Rick's leader irrelevant very fast, even in the word model. Okay, cool question. So, yeah. Any more questions, anybody? Maria still has the hand up. I don't know if that's just
Sorry. Well, I'm still thinking, but I will put it down.
no, but you can ask again.
okay.
That's fine.
Well, I don't know if anyone else doesn't have a question. I don't know if you could
I don't
say.
see a line waiting.
Yeah, I don't know if you could say a little bit more about, just because I'm not expert in quantum free thermodynamics and stuff. What kind of temperature is that?
So, what kind of temperature is a temperature?
Yeah, that temperature
Oh,
that you're talking about.
we're in a cavity, right? So Gibbs states are well defined. So the modes we put them in a cavity to or we add extra regularization. So cases where Gibbs is well defined, but you can think of it as the KMS temperature of the field.
Okay.
Wait, now that you said this, is everything done in a cavity there?
We put
Is
the modes in a
absolutely
cavity.
everything,
Yeah.
Okay.
The computations, there's a part that the plots are generated with cavities, right? Some put out in the paper, right? Generated with cavities. The expression of, but I don't think the argument changes
No.
if you.
No, the
put it in
cavity is
free
not a
space. The
requirement.
expression
It's
is-
just practical.
yeah.
It's not a requirement. It's practical. You can take L to infinity, no problem. Everything carries. All right.
Are there any more questions?
How can we say, actually, I didn't notice anything about cavity. Why do we say that it's in a cavity?
So the Rueb mode is pick a mode that is local. So, okay, we make the whole universe is a cavity of length L. And then we have a small amount that is the Rueb.
The smaller.
It's not the cavity that localizes. The cavity is an extra that is very big.
Okay.
The localization is much smaller than the cavity scale.
I see.
So, some of the paper is done outside of a cavity.
Yeah.
Yeah.
I'm just talking about the plots that we're talking about when we have thermality in particular.
Yeah, when we're talking about temperatures, we generally have a cavity length or a mass scale to compare it to. We regularize with mass sometimes as well.
All right. More questions?
Well, I don't know if you want to say a little bit more about the analogy with the root of it, actually. To me, it doesn't exactly, I don't exactly get the analogy. I get this analogy better than the analogy. You just take the basic...
What analogy?
Sorry, so to say that, okay, there's an intuition that mixedness can harm entanglement harvesting, and then you treat it in the root of it case as pretty much kind of like a separate project.
Yeah, it is a separate
But
project.
I cannot exactly translate, the claims from one to the other.
So the claim from Rueb is that any probe, because it's localized, would have mixedness. If anything, because of Rick's leader. That's what the claim is. We say, okay, let's consider a mixed unrooted width. We don't care where the mixedness comes from. And then we analyze the impact of the mixedness on harvesting. It could have come from Rick's leader, sure. It could have come from anywhere else. In particular, we studied the case that it comes because the probe is hot.
Yeah, so the logic is that the final conclusion that we arrived at, that Rueb arrived at in the first paper, about the limits to entanglement harvesting with weakly coupled local detectors, since it was due to mixedness, which is something that he himself diagnosed, then it should also be able to be reproduced, let's say, with mixedness in the Arrow-DeWitt kind of model, which could come from other sources, as we were saying. But since the culprit was the mixedness, then we should be able to see that in the Arrow-DeWitt model. So that was the.
There are 2 points in the paper, Maria. First point is the Rueb model sucks to reproduce anything physical. And then, since that one sucks, we also analyze how, even though we analyze how temperature impacts that as well, we do analyze and we see that if you put numbers that are realistic, temperature dominates over any ringleader kind of mixedness. You actually see the two regimes in the plots. I don't know, Bruno, you don't have any of the plots here, but doesn't matter. The Rued model in the end, we say, well, it's not a good model to reproduce a detector realistically. But the point is clear. So if you have mixedness, there's unavoidable mixedness in a detector, no matter what it is. Okay, let's get the under the weight and put some mixedness in it, see the impact on harvesting.
Yeah, but it's just how can I say? I get that you're treating mixedness then separately in the vid context, and that's fine. I get that point, but it's just that I cannot follow exactly. If you're saying that this doesn't work because of the shape dependence, but then there's not. So you say this doesn't.
The Rued model.
The Rued, yeah, doesn't work because of the shape dependence.
It's not that it doesn't work.
And then
it's that it's not physical.
You mean that as long as you don't motivate the choice of shape of test function, which is a fair point, then you don't know, like it becomes negligible, this effect that he's talking about.
But let me put it in a different way. It's a really bad model for atomic probes. It may be a model for something else, but it's be extremely dependent on the shape. So you better get a good experimentalist that can shape the things that you want at the microscopic level.
Yeah, but then in the honor de vid stuff, there is also shapes of things like the smearing of the interaction.
Things are like the results are independent of the shape. They are just small corrections if you want. They don't change the qualitative results that we got. Shapes are the honor de vid model is robust and the changes of shape. What is important is the scales, as typically in physics.
And their shape, you're thinking of the shape of the smearing function.
Yeah. Indeed.
Because I mean, well, a big discussion, but in my opinion, some things can depend on the shape of that actually. But
some things do.
But then it's you can try to motivate that shape of the smearing function in the Revit context based on what kind of.
But what I mean by it's not dramatic. The effect of the shape is not dramatic in experimentally feasible regimes. You know what I mean? The shape is less important than the scale. That's what I mean. Much less important.
Okay, less.
If you change the shape, the result will change less than if you change the scales.
Yeah, but you say I'm not even sure that this is what I should have been comparing. The shape of the test function here, of that mode that Ruep is considering, or the shape of the smearing function of the Unruh-David interaction Hamiltonian. You know, so that's what I meant, that I cannot follow exactly the analogy.
We are certainly not comparing the two. No, we don't get the same results and we ascribe the meaning of the. So maybe you're understanding, you are taking the shape that Rued gives and puts it into the smearing. We don't do that. No.
No, I'm not understanding that. But just to that extent, I'm saying that I just cannot compare exactly.
We do two independent things. It's not a comparison even, right?
Okay,
we do two independent things.
Yeah, that I understand. Okay.
It's not meant to be a comparison. Two independent things. Okay. First of all, Rued model, how realistic it is. Conclusion, not very. However, a point that he makes is fair. There would be mixedness, and mixedness hinders entanglement harvesting. All right, let's go to a model that we consider realistic, which is the under the width, and see how mixedness hinders entanglement there. Those are the two things. And we realize actually the hindering of entanglement through a little bit of mixedness is not crucial. It's not bad. It's not. It doesn't do the effect that Rued claim may do. For example, it's not that dramatic. That's all we do.
Okay. And maybe one question about terminology, because these are my favorite questions. Why do you call it a model, like a web model?
Model, a particular application of a framework to model a physical situation is what I call a model.
Just that, so okay, the way I understand the word model in their context is that when they say that they have a framework for measurements, or in general a QFT framework, then a model basically means to fix an interaction Hamiltonian. For example, the model there would be that I take two scalar fields coupled to each other. Now the extra choice of looking at only one mode, so to say, or smeared field operator, that's an extra choice within that model, I would say.
No, the model he uses detectors to in the end is the use of free scalar fields that couple in a region, right? That's what we call the model. So it's the choice of interaction and the choice of fields that you have access to, yeah, that kind of thing. The particularizations of the framework, that's what we use.
But the arrangement of the interaction regions and the processing regions, that's the choice of protocol. which is on top of the model, right?
Mhm.
Is how we're talking. Yes.
And the
Okay,
localization of the
protocol.
interaction and the choice of free scalar fields, I would call it model.
Okay.
Oh no, it's also to distinguish, right, the FV framework from the particular case that group studies, right? That's why.
Yeah, it's only because, I mean, there are, of course, there's extra stuff that Maximilian is doing. It's just that, strictly speaking, as a model, it's already treated in the paper by Fuster and Wertz in just the general sense of coupling two scalar fields to each other.
Yeah.
That's all I'm saying.
Yeah, I tend to agree with that. Yeah, but again, it's the particular model of modeling a situation with two. So, for example, we call the Fermi model for fermionic interactions, right? We call it Fermi model, although point-like interactions, point-like flow interactions are super common in QFT, right? And still we call it that particularization of choosing the fields and choosing the particular instance as a model. I don't know. I think
But perhaps RUA protocol would be better. It's like UDW model and entanglement harvesting protocols, right? That's what we usually say. We don't say entanglement harvesting models, right?
We distinguish model. We call it qubit under the width, and harmonic oscillator under width is often called different models too. So I don't know.
Yeah, but it's like, it's entanglement harvesting protocol, right? You use the models and then you come up with the situation and you study it.
But it's not the harvesting what makes the RUA model a model, in my opinion. It's the use of, is the introduction of the coupling and separated regions. I don't know. It's true.
And it's also
already does it. Yes, but it's this thing.
And it is the structure of the probes that sets it apart as well. It's the fact that the probes are chosen as local models of a free scalar field.
Right.
And that's the so it's not a model. Yeah. So it's a model of the probes as well.
I don't know. If you have any suggestions how to call it other than model, I'll be open to suggestions. It's not just I won't be happy with protocol or procedure or harvesting protocol. No, because
I think we're just being asked to clarify where we're referring to the parts of it which are the model and where we're referring to the parts which are the protocol.
That's very Also, so let me just try to understand this a little bit. I don't know, like more intuitively, like to myself, you know. So essentially, these smearing that you're showing there, these are the spatial profiles of the that you smear with the Klein-Gordon field, essentially, right?
The mode. It's a mode of the field, a mode with that shape. It's a combination. If you want, pick at your basis of solutions to the Klein-Gordon equation, and then make a combination of those that looks like that. That's a mode, and then assign annihilation and creation operators to them. Do a quantization with those modes.
Bruno, could you show V hat and W hat in terms of
so
these things? A mode is just
these are the so V hat and W hat are integrals over space. V and W is mirrored with phi and canonical momentum. So I don't have them both in the same slide, but you get.
Are you familiar with the notion that the word mode Thales, right, used for a particular a particular solution to the Klein-Gordon equation? And as long as you have a complete set of modes, you can do quantization in any basis that you want, and assign annihilation and creation operators to them. So
I'm just trying to see like what happens with the time dependence of this, right? Because of course they're not constant in time, right? They will spread. Everything that you're showing there will essentially spread due to the relativistic nature of the Klein-Gordon field and of this, right? They will get this essentially this integral momentum with the e to the minus I omega kt or I omega kt.
Right. Localized modes spread. That's correct.
And then they will spread. So essentially, like this is actually describing essentially, it's as if someone back at infinity had prepared like a conspiracy.
Not infinity. No. Not really. No. That's what you in your local lab have access to. You assume so.
Yeah, sure, but the only way to actually obtain this, like if you really assume to have a free theory like before you go there and measure, right? It's like what does that is a combination of modes that will conspire to give that shape at a given time.
I think it's a fallacy to present
and then it will spread as well, right?
But Thales, that's a misconstruction, right? Because I don't care. In my lab, I measure a local mode, assuming that I can measure a local mode. I measure a local mode. Of course, that comes from the Big Bang from everywhere else in the universe, but I don't care because I measure in my lab, I measure here. I don't need a conspiracy. I just measure here. So happens that everything that was causally connected with this has influenced this mode. But it's about at an instant, an experimentalist has access to a local mode. Like
Bruno, could you go to the back a couple slides, I think, where you have v hat and w hat in the span of something?
Yeah.
Yeah, okay, so the local mode is v hat and w hat, which commute to 1. And they are this v hat in the span of phi in R. R is a space-time region. There's just some blob of space-time, and the thing can be written as a combination of elements of the algebra of this region. And you could also, of course, write it in terms of things in the past or in terms of things in the future. But there is one time when the thing is localized.
Right. And that's why you do your
In
measurements.
our lab
and your
during our
photo stuff.
experiment.
Your interactions, whatever you want, you know?
Yeah, I just think that really, I mean, okay, guys, I'm just agreeing with your claim that this thing is awful for modeling physical situations.
Well,
because,
actually, your argument, I don't think it makes it awful, to be honest, because your argument,
no, not my argument, but the fact that, like, I mean, smearing a free field does not give any localized thing that we have access in a lab.
no, that's not true.
Like,
So, okay,
we
let me
don't.
play the other side. A quantum optician can tell you that, oh, I'm measuring a mode of the field. I have this transverse mode of the field that lives here, and this is where my photons are, and this is when a wave packet arrives from there. This is the localized mode that I'm measuring.
Yeah.
I would say that's a good model.
I imagine a laboratory which is a big glass box, and you know, photons will come through from the Big Bang, and I can catch them while they're in my box, and
Right.
you know.
Yeah, I mean,
but then you're using the photons to measure photons, right? Which is okay, that's what the rule of model does. Okay, yeah.
Right.
no, I was just thinking that this thing is already like you already can do this in like classically, right? Just because I see a curved black hole right now doesn't mean it's an eternal rotating black hole, right?
Yeah, I would actually argue you don't see a curved black hole. But
No, as in, if you see a rotating black hole out there, you have no reason to argue that it has always been rotating, right?
I agree.
But so essentially, what I think here is that there is no issue with taking a wave packet at some point t, because this is basically part of what we call state preparation, right? So it
has to do with the region of space that you have access to.
So-
The modes. So Alex, this is not about a mode that exists. This is about you. Okay, here in space-time, and this is true. I can say even with the algorithm detector, I could do it. What modes of the field do I have access to? So if I couple my detector with a particular smearing, I can always single out a mode of the field that I'm coupling to. Of course, there'll be a combination of many modes of the.
To me, that makes sense because you're probing that thing. You're not using the field to probe something else. You know, it's really a different framework in the sense, right?
I don't.
So the thing that Dan was saying, for example, with get the photons there and let these photons interact with the other electromagnetic field, whatever that you're trying to probe. Well, okay, I can picture this, but that's not what we do, right? We don't use photons to measure photons.
Right.
We use
Yeah.
like something else. We use a massive field. We use
Yeah, you
atoms.
would
We use
want it-
localized things in the sense, right?
A massive
these things do
field would
not
be a
come
better
out-
model.
You would
Massive
want
But
field.
bound
these things-
states. I don't think what you're complaining about is the localization, because these things are local at a time. You want a bound state or something that's going to stick around and follow a time-like trajectory and like stay with us. You
That's
know?
what we use to measure things.
You
Yeah.
want a bound massive state.
But that could be a field. That could be a
And
massive
that does
field.
not come. That does not come out of massive fields. That of
No.
massive free theories. You know, massive free. That there's no state. There's no localized mode of a massive free scalar field theory that will stay localized forever, right?
If the
Like,
mass, not forever, but if the mass is large enough, it makes the localized for all time long enough. That's the, you know what I mean?
Sure.
Okay.
No, but
I think
I
there-
agree. Ideally, we would use a more complicated
Yes.
bound interacting
And-
theory here. But that's just not.
And Rueb
But that's the
himself
thing
talks
that we
about it.
cannot
Rueb-
properly
If the
describe.
paper is not that Rueb says, let's model things with free fields. Rueb says, no, this has to be something bound of some kind. It's just that for the calculations and for the purposes of showing things, it picks some free fields at some point. But he does
Yeah,
like
I think-
discussion. Go ahead, Bruno.
Yeah, I think there are two criticisms to make here. They're precisely related to this point. So here we focus on the aspect of the mixedness of the initial states. And it is true that if you fix some initial states of time where the mode will be selected, you can make it as localized as you want, like we did here, right? But there was also a second issue that I kind of glossed over here, but we addressed that on the paper as well in a couple of paragraphs. That has to do precisely with another way in which this choice of modeling, particle detector model, fails to be realistic in the way that we want, right? Because as you said, it's going to spread as it evolves in time. And you're going to have to somehow motivate another choice of modes in the future that also localizes it back. And Rueb, like the answer that Rueb has in his paper to that is basically that you can also adapt this model to include some external potential that puts it in a cavity. and so on. He doesn't develop it much further than that because that was not the main purpose of his data points. But yeah, then again, you're kind of recovering the intuition that we have for something that bounds the state of the field. So yeah, but I think that's a good thing to have in mind as well.
Yeah, I really think that that's my main concern with the root model. It's using
Yeah.
free fields to model these bound states, these localized things, right?
Yeah.
That's not what free fields do usually.
Yeah, I mean, if you follow Thaler's argument, right, essentially you can kill this by definition, right? Because you can just say that no experiments use quantum fields as a photodetector, and then we're done, right?
You could argue that every experiment uses quantum fields as a photodetector.
Yeah,
I mean,
they
and
only
then-
have the quantum fields.
And then you have to use interacting quantum fields, but I mean, like, and then that's basically killing the model by construction. Like you don't have to do anything even.
But I mean, like Thales' arguments, it kills, I think, all our work. Because, I mean, if you argue that you can't use free fields because you have to assume that everything was free in the past for the actual situation that you have in that moment to be real, yeah, I don't mean that is.
No, you don't
that
need
is
the
often
minus
used.
infinity, but
No.
the ongoing modes, that's a problem. It's not going to stay localized after you measure.
It doesn't matter. That's the whole point.
but
You
that
only
doesn't matter.
localize when you measure.
Yeah, that's it. If you are, it's like when we use the switchings. If for the equivalent period of a detector to switch on and off, you are able to keep the mode in a reasonable bound, then it's effectively it's localized. It's reasonable to make that assumption. To me, at least, it's like for the span of the measurement, if you make a measurement during 10 seconds, and during those 10 seconds the single mode is not going haywire, then it's fine.
Take a look at where free field goes after 10 seconds, man. It really
Travels
spreads.
about
But yeah,
10
it's
light
like
seconds.
It really
yeah,
spreads.
it's gotta be really fast. But yeah, sure.
I didn't say what is math, so I don't know what.
No,
are
of
you
course,
basing your
but it's
comment on.
like yeah, but we don't have like I don't know. If well, yeah, it's hard to describe these things, right? I mean,
I don't think it's a good criticism, because locally you can assume free fields you can assume you have free fields if you don't have interaction. Like yeah, I don't know.
Okay, I mean, I think that's deviating a bit.
I think that the real issue is that we don't have any free field that is used to probe things in this way, right?
I don't think we have any free field at all, because free fields are invisible to us. So those things don't exist.
Yeah, but not even like approximately free in the sense. I mean, an atom is not a mirroring of the electron field, you know? That's not how things work. Of the free electron field, if you will, right? With no external potential. You have to add external potential, then the actual modes will be localized, and then out of that, you
Again, if we go that rabbit
so
hole,
like,
there's no such thing as electrons. Electron fields, it's not, what's a free electron? That doesn't exist. It's coupled to the electromagnetic field. What's a free photon? It doesn't exist. It's always coupled to fermion fields, charge fields. There's no
yeah, and then you cannot
even an
describe any
electron.
localized state.
What's that?
Unless you add an external potential, you cannot really describe any localized thing that will stay localized, right? Yeah, I agree with you.
Positronium, you can do that.
Okay. Yeah. Well, using the positronium to measure the electromagnetic field, for example, that's a good idea, to be honest.
Agree. Practically impossible, but a good idea nevertheless. Yeah.
Or using the Dirac atom that I've been saying for a while. But yeah.
Dirac atom, is not positronium.
If second quantized one, yeah, but the second quantized one with the external. Well, you can describe an effectively bound state by adding an external potential, right? So
yeah, but it's different degrees of
have that.
effectivity in the sense that the high energy physics will not capture in any case. Anyhow, I think that's pretty much a discussion for this. Unless anybody, Maria, any more questions?
No, I think I'm fine for now.
Perfect. So let's stop the
Thanks,
recording.
it was a nice talk.
Let's thank Bruno again then. Let's talk.